Hi everyone, this is Mr. Patrick Ang, and we are now in the third part of the videos on work done, energy and power. So for this third video, it is on the last concept called power. And I think before we go to the details, I have a video to show you, and this will be a good recap over what you have learned in the past two videos. So this is quite a good video, so enjoy.
In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock. When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt, who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse. This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They're adding energy to the clock at a rate of 2.5 watts. You'd need about 40 times as much to run a bright 100-watt light bulb. Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find an answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.
Right, so I hope you at least enjoyed the video. There's a lot of information, but don't worry, we'll go through the idea of power. So just a quick recap, we went through what's work done. Work done is force times the distance in the direction of the force. Okay, so W equals to F times D. And then in the second video, we covered different types of energy, and we know that energy cannot be created or destroyed, but it's only converted from one form to another. So you will not see energy disappear. You will see energy being transformed from one form to another. So here when we talk about the last part, talk about power, just very simply by formula, it is energy divided by the time taken. It is how fast the energy is used up, or how much energy is produced, depending on what's the situation. Okay, so this is the formula. So, okay, going back again. So for power, the unit for power is watts. As we see in the video, is from James Watt. Okay, watt is spelled with a W-A-A-T, and the letter to symbolize it is a capital W. Energy is the unit for energy is joule. We have learned this before, and the letter for it is capital J. Time taken is in seconds. We do not use minute, we do not use hours, we use seconds. So if you've seen the video just now, the guy had to calculate in seconds, multiplying 5 days, multiplying all the way until seconds to get the amount of time taken. So important that this is in seconds, because we tend to make the mistake here. Alright, so let's try. Again, if you need, pause the video, try it out by yourself before going through the answers from the video. So let's look at what information this question is giving us. So the question tells us that there is 1,000 joules of energy being converted by this machine over 5 seconds. So what is the power of the machine? So the first thing I do, I will put in my formula. So power equals energy over time taken. And then in this case, I know that my energy used is, or energy converted is 1,000 joules. Okay, and the time taken that the machine does it is 5 seconds. So 1,000 divided by 5, I get 200. I can put my answer in joules per second, but the SI unit that I will use here is watts. So 200 watts. Okay, so that shouldn't be too difficult. Let's look at example 2. So now I have a more clear machine. I have this vacuum cleaner. Vacuum cleaner uses electrical energy, converts it to probably kinetic energy, to suck air, and then so that you can actually vacuum the place. So the amount of energy that it converts electrical to other forms of energy is actually 10,800 joules. And this amount of energy is converted within 20 seconds. Okay, in 20 seconds. So what's the power rating of this vacuum cleaner? So power equals energy over time taken again. And we put in the energy divided by the time. Be careful that the time is in seconds. Okay, do a quick check. Okay, this is correct. Put in answer 540 watts. Okay, that isn't so bad, quite straightforward. Now, it's also important to remember that energy and work done are closely related. So for example, like the video just now, when I did work to try to lift the cylinders of the grandfather clock, the energy from my body as I turn it, as the work done, is being converted into the gravitational potential energy of the cylinder. So if let's say I do a certain amount of work, the work transfer the energy and then becomes stored in the object. So it depends on what situation we are talking about. Okay, so we can choose to rewrite the formula. So instead of putting energy here, it's the same as putting a work done here. Okay, so how does this work out? So let's look at the next example. So I have a man accomplished 500 joules of work. Notice this is work now, work done, to push a box across the floor in 20 seconds. Calculate the power of the man. So I do not have energy converted, but I have work done, which is the same thing. So I can still use the formula, power equals work done over time, and then I put 500 joules divided by 20 seconds. So again, here you just put into calculator, quick check, this is in seconds. I get 25 watts, make sure my unit is correct. Okay, let's move on to our last example for these notes. So now a man develops 25 watts of power, pushing a box across the floor. Okay, we have a lot of men liking to push boxes in our examples. And this time in 20 seconds. So calculate work done. So in this case, I am given power, I'm given time, and I'm asked to find work done. Can you do that? Okay, so the formula is this. But this time, we know that the power is 25 watts, so we put the power here. Work done, we do not know, we just put it as WD to represent work done. Time taken is 20 seconds. So now I have 25 watts equals to work done divided by 20 seconds. If it's divided by 20, I bring it over to the other side, it's multiplied by 20. So I have 25 watts times 20 seconds, and I get 500 joules. So this is my work done. The man did 500 joules of work by pushing the box. Alright, so this is the end of the 3 videos on work done, energy, and power. I hope you'll be able to understand and you enjoy the videos. Please remember to write down your questions and then come to class and ask your teachers. Alright, that is all.